start, and then other people will actually continue showing up. So it's a great pleasure to introduce our colloquium speaker for today, Professor Vinod Menon from the City University of New York. And Dr. Menon got his PhD from the University of Massachusetts and then was awarded a Bell Labs postdoctoral fellowship at Princeton. And he spent several years as a researcher in Princeton, and then he moved to the faculty position at the City University of New York, where he is currently a professor, chair of the Department of Physics, our condolences, and also director of the Center for Advanced Technologies. And Vinod does a very interesting interdisciplinary research on novel two-dimensional materials coupled with nanophotonics and nanomaterials applications. So he basically couples these materials to light so strongly that the excitations in the material become the polaritons, half light, half matter. And as a result, they acquire some very interesting properties. They can, for example, experience Bose-Einstein condensation or serve as qubits for quantum information applications. But I probably should shut up and let Vinod tell you about, tell you the story himself. So, they are all yours, please.
Thank you, Alexei. Thank you so much for the kind introduction, and thank you all for coming. And it's a pleasure to be here giving the talk virtually at Texas A&M. I also see my old professor who just joined in. Professor Agarwal was my professor back in India, and some of the quantum optics that I learned is from him. So it's nice to see him in the audience as well. So I'm going to start, let me share my screen, and let me just go to, yeah, there you go. And let me just, excellent. So everyone can see my screen. So I'm going to talk about strong light matter coupling in 2D atomic crystals. I'm from City College of New York. And the work that we have been doing has been funded by the National Science Foundation, Army Research Office, DOE, and more recently a little bit of work from DARPA. I'm also part of a MRSEC center at Columbia, which also works on 2D materials. So just quickly, for those of you who are uninitiated in the topic of polaritons and so on, it's a quick overview of what strong light matter coupling means. So you have a material resonance. It can be any kind of material resonance. It can be an exciton, charge oscillations, lattice vibrations. And you couple that to a photonic resonance, an electromagnetic resonance, and you can hybridize them. And when you hybridize them, you get these hybrid states, which are called polaritons, upper polariton and lower polariton. And these states inherit the properties of both the material resonance and the photon resonance. So that, and these are these half-light, half-matter quasi-particles that Alexei was alluding to. Now, in this talk, I'll focus only on the electromagnetic field interacting with excitons, which are electron-hole pairs that are bound by the Coulomb interaction. Now, when the word polaritons has been around for a while, but historically, the idea of hybridizing material excitations with light has been around for a long time. And in fact, the earliest works on this dates back to 1950s, where people looked at the coupling between the lattice vibrations and electromagnetic radiations in ionic crystals and in rock salt lattices and so on. And then this was followed by work on excitons, where I've highlighted three of the pioneering works by Peker, Agranovich, and Hopfield, all of whom looked at electromagnetic waves coupling to excitons in systems and the effect of that in the case of fluorescence, or what happens to the complex dielectric constant of crystals under these couplings. And then about 10 years later, there was the work from Kretschmann and Otto and others on electromagnetic radiation coupling to charge oscillations in a metallic film. And that is what we now know as plasmons and this field of plasmonics and everything. So all of this can be clubbed under this more general property of hybrid quasi-particles that are created by strong interaction between electromagnetic radiation and material excitations. So how does one create these excitations? So you have this is the simplest case. You have an exciton electron hole pair sitting between two mirrors, and this exciton has a decay rate given by gamma exciton, which is the lifetime, which is dictated by the lifetime of this exciton. You also have the photon, which has a finite lifetime because of the loss of the mirrors, which is given by gamma c, and you have the interaction between the two systems, which is given by the small g. The condition for strong coupling to happen is that this G has to be greater than the decay rates of either the gamma exciton and the gamma cavity photon. And when this condition is satisfied, you enter into the strong coupling regime. Or in other words, what we are saying is that the exciton and the photon needs to exist for times longer than their interaction rates, or the time it takes for their interaction. And if you want to write down the Hamiltonian of the system, it is essentially the Hamiltonian of the cavity, the exciton, and the interaction term. And the interaction term essentially is a term which is standard notation, where A and A dagger correspond to the annihilation and creation operator for the exciton, and the B and B dagger corresponds to the annihilation and creation operator for the photon. So what ends up happening in the strong coupling picture is that you end up getting so this term here is your cavity photon, that is just the cavity dispersion, energy versus in-plane momentum. And you get your exciton, which is given here, which is your flat band. Remember, within the wave vectors of the photon that we are talking about, the exciton can be treated as almost a flat line. And when this happens, you end up, and so you get the crossing of the two modes, the exciton mode and the cavity mode. And if you enter into the strong coupling regime, you get these two new eigenmodes, which are called the upper and lower polaritons. And the other important thing to remember here is that the angle at which the light comes out from a cavity structure such as this essentially is a direct mapping of the in-plane momentum of the system. So you can right away get your energy versus momentum diagrams by just looking at the energy of the photon, so spectroscopically, and the angle at which the light comes out, which you can do either in real space or using Fourier space concepts. So you see here the Hamiltonian is given by this expression where you have the interaction terms in the off-diagonal terms, and you solve for it. And if you solve for the Hamiltonian, you get the energy of the lower polariton and the upper polariton is essentially given by this expression here, where this plus and minus corresponds to the upper and lower polaritons. So this is how you get the two eigenstates of the system. Now, usually you can pump either here, you can pump either at the exciton, or you can pump at the lower polariton. And there has been a lot of interesting physics that's come out from where you pump these systems, including condensation, as was mentioned earlier. So just to quickly summarize, you have an exciton sitting between two mirrors. The mirrors can be metal, it can be Bragg mirrors. Bragg mirrors are just alternating layers of dielectrics, which creates a very high quality mirror. And then the angle at which the light comes out, it relates to the in-plane momenta. And then spectrally, if you resolve it, you get the two eigenstates of the problem of the system, which are now the lower and upper polaritons. Now, what is interesting about this system is these are composite bosons. They have half exciton property and half photon property, right exactly where they, for example, where they cross. And the excitonic component provides you the nonlinearities, the electronic response, scattering, and so on. Whereas the photonic component gives you the spatial mass, the spatial coherence, and the small mass, the spatial coherence, and the long range propagation. And it should also be noted that let's just take this curve, for example. If I start somewhere here at high momenta, my polariton is very exciton-like. It's more massive. And then as I go towards k equal to 0, it becomes very photon-like. So here is a way where I can actually manipulate these components depending on the fraction of the photon and fraction of the exciton component in this lower polariton. In fact, these fractions are now more popularly known as the Hopfield coefficients once you fit these to the Hopfield coupled oscillator model in this case. By the way, please interrupt me if you have any questions. I cannot see the chat window, so if Alexei or Rainer can look at the chat window and ask me questions, I'm happy to answer. Otherwise, please interrupt me and ask questions if you have any. So why were the reason why polaritons or exciton polaritons were very popular in the early days, since their first work by Claude Weisbuch back in 94, was the idea that we could realize condensation of these polaritons. And the idea here is that you can excite the lower polariton and the polaritons undergo scattering, and you can get a population here, which is, and if the population reaches a certain threshold, you can create a macroscopic coherence out of the state, and you can get condensation. Now, it was in those days, it used to be called BECs. People still sometimes use the word BEC. I want to point out that they are not true BECs because, for one, they're not under thermal equilibrium. The polariton number is not conserved. So you're constantly pumping the system, and this polaritons are leaking out of the system. So it's a driven dissipative system in some sense. And it is like Bose-Einstein condensation, but it's not a BEC. Nevertheless, people have observed a whole set of phenomena ranging from superfluidity to condensation, where you see it in both real space and in momentum space. There have been some recent reports of thermalization of these polaritons, where the polaritons live long enough that they can thermalize. And you can also have some 2D electron gases, and in all sorts of materials. More recently, they've even found some applications, like making interferometers with them, and also emulating some of the phenomena like topological physics with these, and also using them as simulators, where the polariton condensates essentially mimic like the BECs that the cold atom people are trying to do to create quantum simulators. There are still problems here, again, the same reason of being not in thermal equilibrium, but one could take that as an advantage and try to emulate out of equilibrium phenomena. On the room temperature side, there is the advantage that there are some classes of material systems where one could do these experiments even at room temperature. And this essentially boils down to the question of whether these materials have a strong exciton binding energy, and if so, can we use them for realizing these strong coupling phenomena. I'm not going to list out these names, but these are some of the materials that are can do these strong coupling at room temperature. So I'm going to focus today's talk on 2D materials, and they don't need much of an introduction. I mean, starting with graphene, there has been a whole huge interest in this field. I will focus specifically on 2D chalcogenides, and these are the molybdenum disulfide, tungsten disulfide, molyselenide, and tungsten selenide. And these are semiconductors, and they become a direct bandgap semiconductor in the monolayer limit. And the reason why 2D materials are also interesting from a broader context of polaritons is the fact that these 2D materials can actually host not just exciton polaritons, they can host phonon polaritons, like for example in hexagonal boron nitride, or plasmon polaritons like in graphene or black phosphorus. And there have been more recently interest in things like Cooper pair polaritons and Magnon polaritons, essentially coupling between material excitation, in this case magnons, and the photons, and in this case the plasmons in the graphene and the photons. So it's a very nice platform to study a whole slew of different kinds of polariton systems and even combining them in some cases. So what happens to these material systems when you make them into the monolayer limit? So this is the layered structure of these materials, and they essentially consist of 3 atoms that form the monolayer, and each monolayer is held together by a van der Waals force. And now, as I go from the bulk to the monolayer limit, what happens is at the K, so it's an indirect bandgap semiconductor at the gamma point at the bulk limit, and as I go to the monolayer limit, the system becomes a direct bandgap, but not at the gamma point, but at the K point of the system. And this shows up nicely if I just did a simple photoluminescence experiment where I take a 2-layer system versus a 1-layer system, and you'll see that the 2-layer system barely emits light, and the 1-layer system emits light which is almost 1,000 times higher than what a 2-layer system emits. So it becomes a direct bandgap and it starts emitting light once you go into the monolayer limit. So then the question comes, why do you want to do exciton polaritons with 2D TMDs, besides the fact that 2D materials are very popular these days? Is there something that really these materials offer? So this is something that our group struggled with, trying to understand separating out the hype factor from, is there really a new science that we can do in this context? And of course, the binding energy is one of them, which is that it's got a large binding energy, zero point 0.1 to 0.3 eV compared to most other semiconductor materials. And this large binding energy comes about because of the reduced dimensionality, weak screening outside the 2D layer. And so you will see that the exciton is well separated from the quasi-particle band gap. Now, if you take a material, you also ask the question about its interaction strength with light. And you see that the interaction strength of this material is pretty large. It's actually on the at the exciton resonances, a monolayer of this material absorbs about 10 to 12% light. And this black line here is graphene, but these colored lines are the different semiconductors. So again, this is almost one of the largest absorption that is available if you actually normalize it with the thickness of the material. And so if you compare it to silicon, which is the most widely used solar cell material, or gallium arsenide, you would need about 50 times the thickness of this monolayer to get the same amount of absorption. And this large oscillator strength comes about because of the highly localized d orbitals that are involved in these transitions. You also have, and although these are tightly bound excitons, you can still describe them within a Wannier picture, hydrogen atom-like picture, where you have a finite Bohr radius, and the Bohr radius typically is on the order of about 1.6 to 2 nanometers for the 1s exciton, to the ground state exciton. And the other interesting thing about these systems is that because the binding energy is so large, one can actually see not just the 1s state, but you can actually see all the way up to about 4s to 5s states of these excitons. Or in other words, these larger Rydberg excitons can be observed in these systems. They also have this interesting property that the optical selection rules are very specific. Or in other words, if I come with a particular handed light, I can excite carriers in the K valley and not in the K prime valley. And if I come with the left-handed circularly polarized light, it's the K prime valley that I excite and not the K valley. And this selectivity that comes from this, or this valley property, comes about because of the broken inversion symmetry in the system. Because although they form a hexagonal lattice, the K and K prime points are dissimilar and have different selection rules. So that's an interesting property. Because the binding energy is so large in these systems, the trions, or the charged excitons, where you have an electron hole pair attached with an extra exciton, also has a reasonable binding energy. So in fact, it's on the order of 30 millielectron volt, which has been measured. So even these are pretty robust at reasonable temperatures in these systems. And they also exhibit very nice nonlinear optical properties. In fact, at some levels, nonlinear optics has become a tool to measure the crystal orientation of these materials. And in fact, you can get these beautiful six-fold crystal symmetry from the second harmonic signal. And again, it also is a nice way to distinguish between monolayer versus bilayer, because in a monolayer there is broken inversion symmetry, whereas if you go to two layers, that is cancelled out, and so you will get a much weaker second harmonic signal. Any questions? Okay. If there are no questions, then the other advantage of this materials is, from a more technical or experimental standpoint, is you can actually stack them up like a Lego, as shown in this cartoon taken from this review article. And you can have all sorts of materials. You can have a metal, semi-metal, graphene, insulator, hexagonal boron nitride, and you can have a semiconductor. So it's also nice that these materials can be exfoliated from, the word exfoliation just means that you're using Scotch tape from a bulk crystal and you're peeling it off. And you can get really high quality material by starting from a good crystal. And in some sense, it has democratized the whole material science involved in these interesting physics discoveries, because you're not relying on high-end MBE systems to create the highest quality materials. You can actually do this by just commercially buying crystals and then just using Scotch tape and peeling it off. You also have the advantage that you can actually stack layers with different band offsets. So now you can get different interactions, for example, a direct exciton, indirect exciton, and so on, that can be done with these structures, very similar to what one does with MBE. So here is a quick overview of the work that we had done in the past. I'm not going to go over everything here. I just wanted to show you that We were able to show strong coupling at room temperature at back in 2015. And then this work essentially jump-started everything else that we have done, where we show that you can show Valley properties of these excitons. We can make them propagate long distances through this strong coupling, and also use electrical field to control whether you go from strong to weak coupling. And this is because when you gate the system, you're producing more carriers. And when you produce more carriers, the screening gets modified, the effective oscillator strength gets dropped, and hence you go from strong to weak coupling. So you don't have enough oscillator strength to couple to light very effectively. But what I'm going to focus today on is some work that we did last year, which came out last year, where we showed that you can take these systems and make electrically driven devices inside an optical cavity. So it's more of a, here you have a bottom mirror, you have a top mirror, which is just a silver layer. And this is my band diagram. So I have a graphene layer, which I can gate and I can change the Fermi level. And I have two very thin layers of hexagonal boron nitride. So these are insulators, which act as tunnel barriers. And so this is about 1 nanometers thick. And then I gate the device and I can tunnel into these layers, and I can create my electron hole pair here, which recombines and emits a photon. And then the whole structure is encapsulated between hexagonal boron nitride to isolate it from anything else outside. And then that is incorporated into the cavity structure. So what we do now is, if you turn on the device, you see the typical turn on voltage where the current starts flowing inside the device and so on. And so we went ahead and made the device. This is just to show you that it's actually, it sounds crazy that you can actually make a tunnel device with a Scotch tape based technique, but it works. And this is just actually picking up these layers one after the other, creating a layer. In this case, we had 11 layers inside the structure, and then you turn on the current and it actually emits light. So this is just to convince ourselves that there is strong coupling. So this is a reflection diagram, this is photoluminescence, and this is electroluminescence. And in fact, if you look at low current versus high current, you can clearly see that most of the photoluminescence is coming from this very small angle here. And this is in momentum space. And so this is just to look at what the dispersion of the structure of these systems are. And then the bottom here is the real space image showing low intensity versus low current density versus high current density, where at high current density you can see that the whole flake lights up. This flake, by the way, this is about 5 microns, this is about 12 microns long. So that's the flake or the actual active area of this device. Any questions?
Can you estimate the radiative efficiency?
Yes, so the efficiency, the electroluminescence efficiency of this device was pretty bad. It was only about 0.1%, but in the context of Polariton devices, it's comparable to other Polariton devices that operate at room temperature in this case. So I won't say that this is the best, anywhere close to the best LED, but I think what I would say is, from a more fundamental standpoint, what we see is that you can populate the lower polariton very efficiently by electrical injection, as compared to photoluminescence, where we often end up seeing these bottleneck effects where the emission happens at higher K values. So by doing electrical injection, we are able to populate the K value. So this is one way where, for condensation purposes, one of the requirements is that can we populate K equal to 0 very effectively? And this is what we are able to show with this electrical pumping experiments. This work is really due to these two guys who did this amazing work of making the device and getting it to work, and also seeing that it actually is still in the strong coupling regime. So with that, I'm going to switch gears and I'm going to talk about some nonlinear optics. So when we talk about condensation and nonlinear interactions there, it's all done at high pump hours. And this is the case with the polariton condensates in inorganic systems. It's the same with the organic polariton condensates. But you can ask another question, and that is, can I do these at very small photon densities? So in other words, can I do something similar to what is called photon blockade, but now with polaritons? Or in other words, I come with one photon, I create a polariton, and then when the second photon comes in, the two polariton state energy is distinct from the one polariton energy, and so you don't get this second photon to get absorbed in this case. In other words, if I looked at the correlation of the photons that come out of the system, I should see some correlation. And if I did a second order correlation experiment or G2 experiment, I should see an anti-bunching phenomenon in this case. And this was, in fact, the first evidence of this was recently shown by the groups, by two different groups. One was from Atachi Mamaglu's group, and the other was Thomas Walz's group, where they showed that they were able to get some correlation slightly lower than 1. So it's only 0.95. So you're nowhere close to the single photon limit, but it's slightly less than 1, indicating that you have some evidence of correlation kind of setting in into the system. So, and this has been predicted theoretically a long time ago by the work of Christian Achueti and others. So what kind of nonlinear polariton-polariton interaction is needed to actually realize this phenomena? So let's take the cavity polariton picture here. And if I now look at the exciton-exciton interaction, so this is my exchange interaction between the excitons. What happens is, as I increase the number of excitons inside the system, my exciton energy renormalizes, it shifts, it undergoes a blue shift, and the result of this is that my lower polariton and upper polariton blue shifts. So now you can think about this as you are sitting here and imagine this to be the state. My one polariton state shift and the two polariton state shifts are different, and that is exactly what I was showing in this cartoon in the previous slide. Of course, there is one other effect which is often overlooked in the case of gallium arsenide and so on, and that is this effect of phase space filling if you talk about in the momentum space, or in real space, one can think of it as I've created one polariton, I'm creating another polariton. How many polaritons can I fit within a real space location? And because I am saturating this process, the result of this is that because the number of polaritons is going to decrease eventually, I'm starting to get a decrease in the overall Rabi splitting. And this is the other effect that can be seen. It can be translated to an effective decrease in the net oscillator strength of the system. So both of these effects happen simultaneously. I'm going to show you that in the case of 2D materials, this effect dominates over this. So we were motivated by this theoretical work from the group of Thomas Paul, who showed that if I created polaritons, and if I was to go to larger quantum number polaritons or in larger Rydberg states, then I should get larger effective nonlinearity. Now, of course, anyone who is in the cold atom background knows this very well, and you guys have been doing this for a long time, which is to use these Rydberg states. Of course, your ends are much larger. So we wanted to ask the question, do we see the same effect? But now remember that in the polariton case, the oscillator strengths are much larger per polariton. So can we see this by going to these larger n values? So I must point out that in these TMDs, you can actually see these excited states. You can see all the way up to like 4s, as I told you. But it also turns out that the interaction strength is proportional to the square of the Bohr radius. But I must also point out that the Rabi splitting is also proportional to the oscillator strength, which of course decreases as I go to the larger quantum numbers. Nevertheless, I should see some kind of a scaling in the overall interaction as I go from 1s to 2s to 3s and so on. And so our goal for this project was not to realize polariton blockade, but to see if there is a scaling that goes with the Bohr radius. And so we made a structure where we took this material called tungsten diselenide, which has a very strong 1s exciton, but it also has a nice 2s exciton, which you can see here. And then we made this device again with the Scotch tape business. This was the theory for this work was done with Thomas Paul, and there was collaborations with Tony Heinz's group and Jim Hohn's group at Columbia and Stanford, and also with Stefan Kenna-Cohen on some of the theoretical aspects on this device. So the bottom line here is we want to make this device, couple it to the 2s exciton, and ask what is the interaction. So here is our dispersion characteristics, which you've now probably gotten used to. And you can see that as I decrease the temperature, my 2s exciton moves into the cavity photon, and I get this Rabi splitting. But what is most interesting is if I pump this device at low pump powers, I get the Rabi splitting. And as I increase the pump power, my Rabi splitting decreases, and eventually I don't even have strong coupling. But this is not the regime that I'm really interested in. What I'm really interested in is where I still have strong coupling, but my polariton branches are now shifting. The upper polariton is shifting down, the lower polariton is shifting up, and this is what happens in this case. Now, what we see here is that so the saturation effect is dominating, but nevertheless at low pump powers I can see this nonlinear effect. So what we then did was to come up with a model where we say that I create polaritons, and this polaritons that create have a finite radii around them because I'm going from 1s to the 2s state, and I can come up with an effective blockade radius. So my Rabi splitting at n density can be related to the Rabi splitting at 0 density multiplied by some area law. And if I look at the 2s and the 1s, the Rabi splitting divided by as a function of density, you can see that my density at which I can get these appreciable effects is much smaller for the 2s state than the 1s, almost an order of magnitude smaller. And in fact, you can extract out my interaction strength, and it is about 4 micro EV micrometer squared, whereas in this case it's about 1 micro EV micrometer squared. So we get about 4 times increase in interaction strength. And this falls nicely if I just compare my Bohr radii of these materials for the 2s and the 1s. I'm going from a 2s exciton has a Bohr radius of about 6.6 nanometers. The 1s exciton has a Bohr radius of about 1.7 nanometers. These two numbers have been experimentally determined by multiple groups, and you get about 4. So it falls very well that you can actually scale the interaction strength of these polaritons by just going to these excited states. So I'm going to stop. Any questions on this?
I'm curious if you could also involve some terahertz spectroscopy to probe not only 2s state but also 2p etc. states.
Absolutely. Yes. Yes. So there has been some proposals on whether we could pump the 2s to 2p transition by some kind of a 2-photon pump. But we haven't done that, Alexei.
No, but this is optical pump. But with terahertz, you could go directly from 1s
Yes.
to 2p.
Yes. 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 No. Yeah. Absolutely. Absolutely. Okay, so I briefly alluded to this idea of valley polarization, where I said that the selection rules for right-handed and left-handed circularly polarized lights are different, and you can excite different valleys. Now, of course, there is a word terminology that's been used in the community called valley coherence, and where the idea is that I come with linearly polarized light, and I can excite carriers in both valleys, and hence the emission that comes out follows the same linear polarization as my pump beam. Actually, Alexei has done some nice work where he has looked at this system at the single exciton limit, where you can get true entanglement between the two valleys. But every experiment done till date has been done at the limit of an ensemble of carriers. So it's just a coherence that is created between the two valleys, and then you get the linear polarization being conserved for the emission that comes out. So people have proposed this as a means to now essentially manipulate this valley pseudo spin on the Bloch sphere. And it's been studied not just in monolayer but also in bilayer, where the things get a little bit more interesting and more complicated to understand, but nevertheless you can get the same linear polarization being preserved. So of course the goal is can I take this valley pseudo spin and now manipulate it in some ways? And one way to do this is to apply a magnetic field. And if you apply a magnetic field, what you do is you lift the degeneracy of these two valleys, and so you get like what is called a valley Zeeman effect. And this lifting of this degeneracy essentially causes a precession of my valley pseudo spin depending on the amount of magnetic field that you apply. So you can get the valley Zeeman is only about 2 MeV for 9 Tesla. So you get a rotation of about, in this case, you can see about 20 degrees with a 9 Tesla magnetic field. So that's what is being typically observed. Of course, there is one other way to do this. You can apply high pump power, which is below the band exciton energy, and you can induce an optical Stark effect. And if the optical Stark effect happens, then also you can get a precession of your valley pseudo spin. But again, you need very large optical pump powers. In this case, 1 millijoule per centimeter squared was required to achieve this valley, the rotation of the valley pseudo spin. Now, what we decided to do was to ask a slightly different question here. So we know that in polaritons, you can utilize the photon component to manipulate things. And if you take a typical optical cavity, there is a splitting of the eigenstate, the TE and the TM modes of the system. And this splitting gets larger and larger as you go to in-plane momenta. So in the context of polaritons, these have been studied quite extensively, and they call it the optical spin Hall effect in the microcavity picture. And what they show is that this splitting essentially results in an effective magnetic field, and this effective magnetic field rotates the polariton pseudospin. So what is shown here is the direction of my effective magnetic field, and then these red, blue, and the magenta arrows are the direction of my polariton pseudospin and how it rotates. So if you can take one example here, you will see that my effective magnetic field is pointing in this direction, and my polariton pseudospin was here, and now it precesses and goes towards SZ, and the opposite in the other case. So these are cartoons that I've taken from this nice article from Shelik and coworkers, which shows you how one can manipulate the polariton pseudospin by invoking this idea that you get a pseudomagnetic field due to this TE-TM splitting. So and this has been studied in, even in an empty microcavity. If you just looked at it in the K space, you will see that the sigma plus and sigma minus just goes in the opposite directions. So what we did was to do the same thing. Now we take the Polariton system and we look at the degree of linear polarization as a function of in-plane momenta. So what we see is that the degree of linear polarization actually drops. It's not that it is dropping, it's that actually the linear polarization is rotating. And so if I look at it in the same basis as where I'm pumping, it actually seems like it is decreasing. In fact, you can do better. If you project it onto the kx, ky plane, what you see is that you get a rotation of about 15 degrees as I go towards larger angles. So you can see here in the kx, ky plane, out here, they are pointing in the same direction, so there is no rotation. And then I go to 45 degrees, where I should expect the maximum rotation of my polariton pseudospin. My valley coherence, or in this case, the valley exciton polariton, also undergoes the same rotation. And then I go back to 90, it stays the same, and so on. So I guess the take-home message I want to give here is, by strongly coupling to the cavity photons, I'm able to utilize the photon component to manipulate my valley coherence properties in this case. And I'm able to do this without the use of a magnetic field or the use of a large optical pump power, but just by designing a cavity where I have an effective pseudomagnetic field that is coming about because my TE and TM modes are split. This work was spearheaded by my graduate student Mandeep, So now going to the question of condensation and whether you can do condensation in these systems. The short answer is we have not got condensation. But what we do see is that we do get more population at k equal to 0. And we can see this much more clearly here, where you can see that as I increase the pump power, I can get more population at k equal to 0 at 0 degrees compared to larger angles, or in other words, indicating that I have more effective scattering of the polaritons to k equal to 0. So I guess what I want to convey here is we haven't got condensation, but I think these systems can actually condense, and we do understand the bottlenecks. In the early days, it was more material properties, but now it is more about getting good cavities to get this condensation going. Any questions?
In this pseudomagnetic field manipulation, is there any way to estimate the coherence lifetime of the valley coherence?
No, I don't have any estimate on that, Alexei. And we haven't. This was, of course, done in the experiments are all in the ensemble limit. But it's an interesting question. I don't know the answer to that. Okay, so now switching gears to nonlinear properties. I told you these have got, so I'm just going through that set of 6 boxes that I had about why do polaritons with TMD. So I'm on to the last topic here, which is second harmonic generation. So we know that second harmonic generation is pretty efficient in these systems because they have broken inversion symmetry in the monolayer limit. In fact, if you go as a function of layer number, you can clearly see the second harmonic jump, because you're going from something that is non-centrosymmetric to centrosymmetric, non-centrosymmetric, and so on. And so there has been a lot of interest in whether we can enhance this. But it turns out that these materials actually provide a very interesting feature, which is even without a cavity, just by taking a bulk of this material, so it's not a monolayer, it's a bulk, you can create a Fabry-Perot mode within the system. In other words, light can get trapped inside this structure. And because the refractive index is so high in these materials, they can actually couple to light directly. So you can get a self-hybridized polaritons in this system if you choose the thickness correctly. And in fact, this is experimental data. This is simulation just showing that you can get these hybridized exciton polaritons. There is no cavity here. It's just a bulk of this material. And so the question comes, of course, they don't emit light because they are indirect band gap, but we wanted to study the nonlinear properties. So we went ahead and did second harmonic generation on the system. And what we see is, if I just take the bulk where I do not have these polaritons formed, then the bulk signal is below our noise floor. But now when I get the polariton, get it into the strong coupling regime, my second harmonic signal just shoots up. And it's several orders of magnitude higher. This is just one of the spectra. These days we have got going from 1,000 all the way up to about 100,000 in the second harmonic signal. And the power dependence is clearly follows the, it's to the power of 2. So you can know that it is actually second harmonic. So the question comes, why is this happening? And I don't have a clear answer as to why this might be happening. This is very recent results. We do think one of the things resulting in this is, although this bulk has effective centrosymmetry, once you have strong coupling and the polaritons inside the system, it's likely that the gradient of the field starts playing a role, and in some sense the effective response doesn't cancel out, and so we are getting a residual response from these systems. That is our current understanding. There is some theory being worked out, but we don't fully understand. They still show the same value, the helicity properties, and you can see here that the second harmonic signal, when I pump at resonance, is the highest. If I move away from the polariton, it's weaker on both sides. So this is a cute result where we are able to see that you can actually get second harmonic signal from a bulk medium, which normally should not have second harmonic, but it's coming once you get into this strong coupling regime. And I'm open to discussion on this because we're still trying to understand why this might be happening. And in the last 2 minutes or 3 minutes, I want to just quickly talk about some work we have done with Professor Agarwal's group, where we've looked at what happens to these 2D materials when they are placed in the near field of a hyperbolic material. So for those who do not know anything about hyperbolic materials, these are highly anisotropic materials in dielectric constants, and they have, for example, in this regime, where in this part, which is called 4 here, you can see that the real part of the dielectric constant is positive for one direction and negative for the other direction. So the perpendicular component is positive, the parallel component becomes negative. And this results in a hyperbolic dispersion of the, and if you plot the isofrequency contour, it has a hyperbolic dispersion. And there's been a lot of study in what happens when you go from the typical dispersion characteristics to the elliptical characteristics to the hyperbolic dispersion. There is these singularities that arise and so on. But one other property of these materials is the fact that if the emitter is circularly polarized, so if I have a linearly polarized emitter, then the emission follows this conical trajectory, and that is shown here in this line cut or in this field distribution. However, if I come with a circularly polarized emitter, then the emission is preferential in one axis or the other. And you can see that it goes in this case, and in this case, you can see that it is not as clean. So this is what was shown by the Zayat's group back in 2014 using microwave hyperbolic materials. So we asked the question, can we do the same thing with TMDs? But now we know that the TMDs, if I come with sigma plus light, then I should get mostly sigma plus emission. And if I image it in the Fourier plane, I should get the angular property. And this is just numerical simulations that show that if I come with sigma minus, I should get more sigma minus. If I come with sigma plus, most of the sigma plus should come on this direction. So this is what we set out to do. And this is, I'm just going straight to the final results. We don't get a very high contrast. Nevertheless, you can see that if I come with sigma plus, more light comes out on one direction in the, so these are line cuts of this. I get more sigma plus. If I come with sigma minus, I get more emission in the negative K value. And this agrees very well with the numerical simulations carried out by Professor Agarwal's group, where we see the same effect. Of course, in numerical simulations, the contrast is much higher. So this is a nice way to manipulate or control the direction of flow, or extract out the directional flow of these valley excitons using these hyperbolic media. And so I think with that, I want to summarize the work we have done. We've been able to show strong coupling and the valley polarization properties. We've done electrical control, where we see, and also the electroluminescence from these polaritons, and then the Rydberg exciton polaritons, where we see that you get strong interactions when we go towards these excited states. And then the controlling the valley coherence using the pseudomagnetic fields was an interesting result that we just recently got. And this opens up the avenue of using photonic structures and with designer properties to actually now control the excitons in these 2D materials. And of course, none of this would have been possible without these wonderful students. This is a pre-COVID photograph, and the guys who did some of the work, the SSG work, was done by these two guys, Raslin and Mandeep. The Rydberg exciton polaritons led by Jay. The LED work was led by Bishwanath here, and some of the others are more recent entrants into the group, and hopefully we'll see some nice results from them soon. And with that, thank you all for your attention, and I'm happy to take any questions. And these are some of the publications from my group.
Thank you very much, Vinod. Any questions, please? You can just unmute yourself and ask them with your voice.
Can I ask a question?
Yes.
Sure, please go ahead.
When you were talking about the pseudo spin and rotation of that, right?
Yes.
In valley degree of freedom. So is it uniform always, or can you like say excite a pseudo spin wave in that system?
When you say is it uniform, so the magnetic field, the pseudomagnetic field is changing as a function of in-plane momenta, right? Because the TE-TM splitting is changing. Now you're asking if I create this, if I create a polariton, and if I'm looking at the propagation of this polariton, will this polariton see different pseudomagnetic fields as it goes along? Is that the question?
No, not really. What it's a pseudo spin, right? So
yes,
you're supposed to have some sort of pseudo spin waves.
Yes, yes.
It means that in different places in real space, that the direction is a little different, right? And you see.
Good question. Good question. Yes. Now I get it. Yes. So the answer, I did not show the data. It's very preliminary, but we do see directional flow, depending on the helicity of the light that you're using to excite in the cavity. Yes. So we did not. The thing was, we did not use a cavity like this because it was harder to study it, because you have two mirrors on top and bottom. We used a system where you only had a bottom mirror, and we coupled it to a block surface mode, and we watched the propagation in the block surface mode, and you can see it propagate in the two different directions. Yeah, so it's like a spin Hall kind of effect. Yeah.
So you can actually see the speed of the propagation, and so you know what's the exchange field or whatever. Can you like put it in spin language?
Yes, I think you should be able to do it. Yes. So like I said, we just did the experiments where we clearly see that we pump with a certain handedness, and that handedness goes away in one direction, and then you come with the opposite handedness and it goes in the other direction. No electric field applied here. So it's just because of this property that you're just alluding to. Yeah, but we haven't done the calculation, and there's no theory on this yet. It's just purely experiments at this. We've just done some experiments on this. Yeah.
Okay. Arjun, I'm surprised you did not ask a question about these fermions. Can you make some topological non-trivial pattern of
You just interrupted me exactly when I was trying.
Okay.
Right? So yes, of course, the next question is, can you do the fermion of the pseudospin? and see how it's two-dimensional, right? So you do have some topological excitations.
Yes.
They sort of
on that front, one of the things everyone is trying to do is now to actually create a photonic structure which has some topological property, like a Kagome lattice, and then coupling those modes to these excitons. And then you can get these exciton polaritons now, which actually have this property. And there are two papers that have recently just shown that you can couple to them. But what both of them are lacking is the fact that the reason you want to go to polaritons is because there is interactions. And if there isn't, but both these papers don't show the result of the interactions. But it'll be interesting to see if the interaction physics brings out something which is very similar to what we see in condensed matter.
Yeah, and the last question which I have is actually, so you treat that exciton as if it is boson, right? But it's a composite particle. It's two fermions. Is there any difficulties because of that, or I'm just not familiar?
So just at the very basic level of exciton physics, it all works out fine. Where it gets very interesting and where you need to worry about the fermionic picture is in these TMDs, when I start gating them and I get more and more charges into the system, then what the exciton now sits in a Fermi C. So what I really have is a Fermi Polariton, which I'm coupling to. So there is some papers on this from Eugene Demler and others, but some people call it trions. So they look at it as a charged exciton, but I think the picture is not exactly correct because it's not like it's a charged particle that I can move with an electric field. It's still an exciton, but it's an exciton that is dressed by this Fermi C. That's the way, at least I see it.
All right.
But eventually you should experience some kind of the mode transition, right? I mean, route through trions or by excitons. It's eventually the route to your phase space. And
yes, at very large pump powers. So like right now we do all these experiments at very low pump powers, but if you go to very large pump powers, you should see the mode transition. Yeah, absolutely.
All right, thank you.
Yeah.
Very good talk, thanks.
Thank you.
More questions, please. More questions? May I ask maybe a follow-up question if some people are still thinking. So when you put more and more of this, of the polaritons in the cavity, can you control the sign of their interaction energy, interaction constant, or you are doomed, it's always the same sign?
So again, in the pure excitonic case, we haven't seen a shift in the sign of the interaction, but it's been predicted that if I can couple to the trions, the cavity, if I create polaritons with trions, then I should be able to switch the sign of the interaction.
I see.
And people have, now there are some results, recent results where the coupling to the trions is possible.
I see.
So there you can see this going from repulsive to attractive thing.
Okay. Yes, please. Yes.
May I ask you, these are your excitations, exciton, polariton. They are bulk excitation or they are propagate near boundaries?
These are, so the excitons that I've studied right now are all free excitons. They're not bound excitons. They're not localized in space. So they are delocalized in space. You can create confinement and make them localized excitons if you have some kind of defects or if you introduce strain. So then you can create localized excitons. More recently, people have been interested in this whole idea of moire, where you take two of these layers and twist them and you get a moire pattern. And then in that moire pattern, what happens is the moire minimas essentially act as localized excitons or create localized excitons. So the nice thing is in these systems, you can actually go from excitons that are not bound to highly localized excitons. I assume what you meant by bound is bound in real space, correct?
He
like
actually asked bulk.
I have in mind the boundary of your sample. You have a film.
yes.
And,
No, these are sitting everywhere. These are everywhere. These are everywhere. Wherever I optically excite, I have excitons.
But in 2D, of
In
course,
2D,
everywhere.
exactly, in 2D.
They are
Yeah.
propagating freely in 2D.
mm-hmm.
All right, any more questions? Well, if there are no more questions, I think we had a lot of questions already. So let's thank the speaker again. And
Thank you all. Yep.
Yeah, I'm sure that if you have any questions afterwards, then Vinod will be happy to answer by mail or any other way. And moreover, we will stay for a while on the Zoom. So if you want to ask something else, then just please rejoin us. And for now, okay, let's adjourn our meeting. Thank you guys all for coming.
Thank you.